Let's talk about phase change, which is also called change of state. So here we have some solid argon, and if we heat it up, the temperature increases and it turns into liquid. So now the atoms have higher kinetic energy because the temperature's gone up, and they also have higher potential energy because it's become a liquid. And now we heat it up a little bit more and it turns into a gas. So in a gas, the molecules are moving very fast, the kinetic energy is higher, and also the potential energy has gone up to become zero. So earlier it was actually negative potential energy, but now they have zero potential energy. And then we can go backwards and cool it down until it becomes a liquid again, and then we cool it down once more until it becomes solid. So this is what phase change is all about. And we can obviously do it for other materials as well. So here we have some oxygen, which is made up of 2 oxygen atoms in each molecule. And when we heat it up, it became a liquid and then a gas. And then we cool it down, and I don't even think we can see the liquid state because we're cooling it down so quickly that it's just becoming solid straight away. And things are lumping together, and there you go, that's solid oxygen. So we found from these simulations that there are basically 3 different phases or states. So we've got solid, liquid and a gas. And when we're adding energy, we're going to go either from a solid into a liquid or from a liquid into a gas. And when we go the opposite direction, it has to be the opposite, which means that we're removing energy from the material, or the material is releasing energy, when we go from a gas into a liquid or from a liquid into a solid. Now if we look at the energies of the molecules in these 3 different phases, we find that in a solid the molecules have the least potential energy, and in a gas they have the most potential energy, and a liquid is somewhere in between. So when we're adding energy from a liquid into a gas, for example, the molecules are gaining potential energy, and that's why they change phase. So let's look at phase change in this simulation. So we're starting with liquid chlorine, and now we heat it up. And if you look at the graph on the right, at first the temperature went up when we were heating it up, but now the temperature is staying constant even if we're adding energy. And the phase of the chlorine was also changing from a liquid into a gas at that point. And then afterwards, when we heat it up, the temperature goes up again. And let's try the same for bromine. So we've got the same graph. So in the beginning, we're heating up the liquid and it gets hotter. But now when we reach the boiling point, the temperature is no longer going up. But we can see that the potential energy of the molecules is increasing because they're now flying around more and it's become a gas. And then once it's a gas, again when we're adding energy, the temperature increases. And finally for iodine, let's do the same thing. So we got liquid iodine and the temperature went up, but now the temperature is staying constant because it's changing phase. So we're at the boiling point of iodine, and it's still just adding energy but not getting any increase in temperature. And there, now we're finally getting a bit of an increase in temperature. So what we can see on these graphs is that while we're adding energy, we're either getting more kinetic energy, which shows up as temperature, or we're getting more potential energy, which changes the state. So whenever the graph is flat, that means that there's a phase change going on. So the kinetic energy is not increasing, only the potential energy of the molecules. Now let's draw our own graph of phase changes. And we're still going to have temperature on the y-axis, and we're going to have in degrees Celsius. But along the x-axis, we're going to have time instead of energy. And our temperature is going to go from -50 to 150 degrees Celsius, because we're going to start off with ice at -50 degrees, and we're going to heat it until we have steam at 150 degrees Celsius. So our heater has a constant power, so output power. So every second we're adding the same amount of energy, which means that we can put our time axis instead of energy to see what happens with respect to time. So when we turn on the heater when the ice is -50 degrees Celsius, the ice is going to increase its temperature until it gets to 0 degrees, because 0 degrees is the melting temperature of water, or of ice. I guess it's the ice melting. So once the temperature of the ice gets to 0 degrees, it starts melting. So all the energy that we're adding at this point is going into potential energy of the molecules, and as that increases, it becomes liquid, so it becomes water. So we're starting with ice whose temperature is increasing, and then we've got constant temperature while the ice is melting, and once we have water, where the temperature is going to be increasing again, and when the water starts boiling, the temperature is going to be 100 degrees Celsius, and it's going to stay there. So even if we're adding energy at this point, the temperature is not increasing because we're giving the molecules so much energy that they can leave the liquid and become a gas. And when we've added enough energy, then the boiling will stop, and the whole of the amount of ice that we had in the beginning, and then water, has now become steam. And the steam is initially at 100 degrees, but as we heat it up more, it increases its temperature, and then when we get to 150 degrees Celsius, we stop. So in terms of energy, what we did was we were adding energy all the way from ice into steam, but we could also go the other way around and go from steam back into ice by removing energy. So we noticed that during a phase change, there's actually no change in temperature. So during melting and boiling, we can see that the line is flat. And while we have ice, water or steam, there is a temperature increase when we're adding heat. But the gradient of the temperature increase is actually going to depend on the specific heat capacity of the material. And it would be steeper if we had a lower specific heat capacity, and it would be less steep if we had a higher specific heat capacity. Now let's jump over to something else that's to do with phase change, and it's the difference between evaporation and boiling. So here we see some water with some internal energy, and you saw there that a bit of internal energy left the water and went into the air. And that might be because a molecule jumped from the water, the liquid state, into the gas state, so it actually became gas even if the water wasn't boiling. And that's called evaporation. And we can increase how often this happens by adding more energy to the water, so the water is hotter. Let's do a little bit more before the boiling temperature. So you can see it started boiling there a little bit. Okay, so let's let the water boil and see how that's different. So when the water's boiling, you can see that the temperature is constantly at the boiling temperature because I keep adding heat, and the water's losing lots of energy and lots of molecules into the air. So the two main differences between boiling and evaporation are that boiling happens throughout the liquid, whereas evaporation only happens at the surface. And the other main difference is that boiling only happens at the boiling temperature, whereas evaporation can happen at all temperatures. But that doesn't mean that evaporation always happens at the same rate. So there are a few ways that we can increase the rate of evaporation. One is to increase the surface area, because as we said, evaporation only happens at the surface, because molecules of higher kinetic energy jump off the surface. So if we have a bigger surface area, that's more likely to happen. So that's one way of increasing the rate of evaporation. And the next one is that we could increase the temperature, because if we have the same liquid but at a higher temperature, then that means that the average kinetic energy of the molecules is higher, so we're more likely to get a molecule that has a high enough kinetic energy to jump off the surface of the water altogether. And finally, we could blow across the surface of the water. So that means that the amount of water vapor in the air just above the surface is going to be less because we're blowing it away. And that means that there's space for more water vapor to come into the air.